Salam sejahtera and a good day. In this session, we shall be talking about regression. Regression investigates the relationship between a dependent variable, y, with one or more independent variables. It allows us to build regression function, which is actually a mathematical formula describing the relationship or relationships between y and x's that can be used for prediction and forecasting. So how is regression different from correlation? You have to remember that correlation look at retrospective data, and whereas regression look at predictive data. That means regression actually look ahead of time for prediction, whereas correlation look backwards in time for events that has already happened or relationship that has already been established. So based on that, regression can be used for all kinds of applications. For example, in compass model to predict growth and so on and so forth. So compass model originally started at Boeing Corporation in around 1960s, and it was originally used for engineering purposes. But then it has found its application to model growth of tumor and organisms, even in the area of finance, and of course, to predict the durability of aircraft parts, and so on and so forth. So the types of regressions are as listed follows. So first will be the simple linear regression. This allows us to investigate the relationship of one dependent and one independent variable in linear terms. Multiple linear regression, which shall be covered in this session as well, investigates the relationship between one dependent and multiple independent variables designated as x in linear terms. The third form, which is actually the logistic regression and not going to be covered in our syllabus, involves the investigation of the relationship between one dependent variable that is categorical with one or more dependent variables. So if the dependent variable has only two categories, then it is known as a binary logistic regression. For example, it is being used to determine factors influencing decision to enroll in the DVM program, because your outcome will be either enroll or do not enroll. And in the event that the variable has more than two categories, then that type of regression is known as multinomial logistic regression. For example, you could be determining the food choices of orangutans in the wild. So the orangutans could be given leaves, fruits, and maybe other supplements. And thirdly, if the variable has ordered rank categories, then it will be known as ordinal logistic regression. For example, you could be comparing the prevalence of incidence of cancer across different age groups. You may want to categorize your age group as young, middle age, or maybe senior citizens. Important assumptions that you must adhere to before performing simple regression is actually as listed as follows here. There are 5 of them. And this is also one of the main reasons why regression is so often misused. If we are performing simple regression, then the first assumption should be that there should be a linear relationship between x and y. Secondly, there should be multivariate normality, meaning that x and y must both be normally distributed. Otherwise, you may need to revert to other form of regression. Number 3, there should be no or little multicollinearity. Multicollinearity is also known as collinearity, meaning that two or more independent variables must not be highly correlated. Remember the example whereby we are trying to correlate height and BMIs? That is actually a very good example of collinearity, because BMI having a component of height will for sure will have high degree of collinearity with height. And number 4, there should not be any autocorrelation, or values must be independent. So autocorrelation is a phenomenon whereby variable autocorrelate with itself in a series or at different points in time. This can be checked in SPSS using a statistics known as the Watson-Durbin statistics. However, we have to note that SPSS does not provide a critical value telling us whether the Watson-Durbin is actually indicating autocorrelation or otherwise. And we may have to refer to external table. The value of Durbin-Watson Durbin-Watson statistics ranges from 0 to 4. And as a general rule of thumb, residuals are uncorrelated if the Durbin-Watson statistics is approximately 2. That means between 1.5 to 2.5. A value close to 0 indicates strong positive correlation, whereas a value of 4 indicates strong negative correlation. So remember, we need the Durbin-Watson values to be between 1.5 to 2.5. And last but not least, similar to what we already encountered in t-test and ANOVA, there should also be assumptions of homoscedasticity, meaning that the dependent variable exhibits similar amounts of variance across the range of values for an independent variable. And this is actually, of course, not conformed to when data sets as outliers, which is why we need to perform a residual analysis. And typically when you have outliers, it will be indicated by large residuals when you perform residuals analysis. Now, let's perform simple regression. Predict the final marks for VPP 3160 using marks from test 1. The data is given as follows. So this is actually an exercise allowing us to use data from test 1 to predict what will the students get in their finals. So in order to do that, we have to key in the data, and then after that, go to Analyze, Regression, and of course, click Linear Regression itself. Recall, how do you need to key in the data for regression? The predictor or independent variable goes to the independent section, whereas dependent variable or what you want to predict goes to dependence. And then after that, click on Statistics. After clicking on Statistics, choose Estimates, Model Fits, and Descriptives to further characterize your data. And then we can continue to analyze. This will be the output for our simple regression. The first table is actually the descriptive summary of how many pairs of data that we have redone. Remember, this is simple regression, meaning that we only have one predictor and one independent variable and one dependent variable. So in this case, we can see that all 25 pairs are included, and then they are inclusive of overall marks and test 1. Our main aim is actually to use test 1 to predict overall marks. The next table summarizes the correlation between the two variables. This is where we mentioned earlier in correlation that correlation will actually allow us to predict, to be used for it to use its value to predict future relationship via regression. So in this case, note that the overall marks is significantly correlated with test 1 marks, meaning that we shall be able to, based on this kind of relationship, to predict what type of marks, how many marks that students will get once test 1 is known. So the next table tells you all variables are valid and included. And this table will be important in multiple regression models. So this is actually something that is important, telling you that the data has been included using the default method, in this case listed as enter. Now recall that simple regression is actually simply following the equation y equals ax plus b. And the output actually allow us to build that regression equation. So in this next table, the summary of the model fit is actually when test 1 is used as a predictor, and it also tells us how good the model is. So you can look at the R value here in this case. The R value is actually 0.638 with an R square of 0.407. The adjusted R square is actually 0.381 with a standard error of estimates about 5. So in this case, we wanted a high predictor value. It tells us that it is actually reliable. And then the next table, which is actually an ANOVA table, tells us that predictor test 1 has a significant effect on the dependent overall marks, meaning that the test 1 actually has significant enough to be used as a predictor. Okay, so it's indicated by this particular regression. So what you actually wanted is actually a regression equation that has significance. If your regression equation doesn't have significance, that means it cannot be used to reliably predict relationship between all parameters indicated here. And the final table actually tells us how to write the regression equation based on the relationship known here. Bear in mind, you have test 1, which is actually equivalent to your x, and then your constant will be your the actually the intercept on the slope on the y-axis, and of course you have your standardized coefficient, which you actually use to determine the reliability of the overall regression itself. In this case, you also have the slope value here, which is 1.8, and this is actually the error value. So I want you to remember, simple regression follows the form of y equals ax plus b, whereas a is actually given by your predictor b here, and then again, your constant is given by this constant value here, 47.52. And this is actually how you describe the relationship between the dependent variable y and the predictor x, in this case, which is actually test 1. So you can put everything together, and therefore we get the equation of overall marks equals 1.801, which is actually the unstandardized coefficients b for test 1, plus 47.521, which is actually the constant. And of course, we also need to further investigate. Remember the 5 assumptions for simple regression. You may also want to go back to the statistics menu and click Durbin-Watson to determine that our values are actually not autocorrelated in this case. So remember, in order for the values not to be autocorrelated, the Durbin-Watson's value is supposed to be between 1.5 to 2.5. If you look at this table, we're fairly sure that the values are not autocorrelated because the Durbin-Watson's value is 1.928. And these Durbin-Watson values can also be compared against a custom table here. And this custom table is easily downloadable from the internet. But in this case, it merely reinforces our assumption that there is no autocorrelation. So this table is actually just included in this text to show you, to further confirm that the value between 1.5 to 2.5 for a Durbin-Watson statistics actually tells you there are no correlation among the values used in this particular analysis. So in this case, you can see the conclusion is, therefore, the values are not positively autocorrelated as indicated by this particular table here. And we also need to determine whether they are big outliers or not, as indicated by the residual statistics. So as you can see here, we can see from the standard deviation and then the residuals itself, indicating to us that the values are actually within range, and therefore there are minimal number or maybe none big numbers. They are lying out and away from the main body data. Next, we move on to multiple regression. In order for multiple regression to work, we will require at least 20 data sets to be dependable and valid. And the important assumptions for multiple regression is actually similar to linear regression. Since there are multiple predictors or X's, an important assumption is that no multicollinearity is adhered to in this particular model. And this can be checked using, number 1, Pearson's bivariate correlation among all independent variables must be smaller than 0.08. Number 2, the tolerance value, which measures the influence of one independent variable on all other independent variables, is defined as T equals 1 minus R square, whereby you wanted T that is less than 0.2, which might be indicating that there are multicollinearity in the data, whereas T less than 0.01 definitely confirms collinearity in the data. So the tolerance value is actually something that you can use by looking at by roughly estimating from the value of R square in this case, so that we will know whether we have multicollinearity data or not. Remember, in this case, you will have multiple predictors. Number 3, variance inflation factor, or VIF, of the linear regression is defined as 1 over T. Again, we are looking at the tolerance value. So therefore, VIF of more than 10 indicate presence of multicollinearity. So you see, in this case, both the t-value and VIF value allow us to detect multicollinearity, which further degrade the ability of multiple regression formula or model to predict an outcome. And finally, the condition index, which is calculated using a factor analysis on independent variables. Factor analysis is actually not covered within the syllabus of this particular course, and therefore I shall not be delving deeper. But in this case, values of anything between 10 to 30 indicate a mediocre multicollinearity in the regression variables, whereas value of more than 30 indicates strong multicollinearity. So you have to remember, when you have multiple predictor, multicollinearity will be an issue to the overall multiple regression model. So all these diagnostics are known as multicollinearity diagnostics, and they are also available in the statistics manual. So what are the key steps in multiple regression? Step 1, we need to analyze the correlation and directionality of the data. Number 2, we should estimate or build a model to see how good the regression equation fits. Remember, multiple regression is actually not a single pass analysis. You may need to do a multiple pass analysis and entering your data in different sequence to see how the data behave. And then after that, we may need to evaluate the validity and usefulness of the model. Let's say checking for multicollinearity or comparing or reading the Durbin-Watson values. Of course, this multiple regression has multiple uses. It can be used for causal analysis. That means associating disease agents with a disease or outcome. Forecasting an effect, what will be the magnitude of response if antibiotic dosages is increased? Well, maybe double or triple. And of course, we can also perform trend forecasting. How would the demand for rabies vaccine change once Malaysia no longer is no longer rabies free? So in this case, definitely, this will actually allow us to predict all kinds of scenario, provided that we have all the predictors in place. This is actually an example that allow us to determine whether the birth weight, win weight, or the post-winning average daily gain is a better predictor for slaughter weight in a group of porkers. So as you can see here, the values are given as BW, WW, ADG, and SW, slaughter weight. So you can key in the data as is within the data sheet of SPSS. The analytical steps will involve analyze regression, linear regression. So in this case, even though we invoke linear regression, it will actually allow us to put in a multiple predictor or independent variables here as indicated here. So it's actually important for us to put in the values, the variables here, and then click the appropriate command so that we can perform the analysis that we want. So you can actually click statistics and then click estimates, look for the model fit, descriptives, collinearity diagnostics as what we already looked at, the t-value, the VIF, and all kinds of things. And of course, we also need to look at the residuals by interpreting the values of the Durbin-Watson, which we already covered in the simple regression section. And in this case, as I mentioned before, regression is involve multiple paths of data entry. In this case, it's best that we ensure that our data is entered in a stepwise manner. So that means it involves entering animal number 1, animal number 2, animal number 3, and so on and so forth. And with each of the variable added in cumulative function on top of one another. So once you have done that, we also need to define other analytical parameters. So in this case, click options and check the following. So define how we are going to include variables in our regression model, and then followed by plots so that we can check for homoscedasticity and normality of the residuals. Now, when we look at residual analysis and we look at the plot, we want the plot to be randomly distributed, saying that the data is actually normally distributed. And in this case, make sure that the standardized predicted value or Z residual value, predicted value is in x-axis, whereas standardized residuals or Z residual value is actually in y-axis. This is actually how we determine the behavior of the residuals and see whether they are conforming to normality or otherwise. So in this case, this is actually becoming more important for us to look at what will be the further options involved in this particular linear regression analysis. The results from the multiple regression analysis. First and foremost, note that all 4 parameters are actually included in this analysis, together with the number of data sets included here. It is always important for us to remember how many parameters are actually included and how many are actually being discussed or being compared in subsequent analysis. Do recall that we asked the computer to enter the data in both enter, which is actually the default mode, and stepwise mode, as indicated in the slides earlier. So based on this, what we can say is that the Pearson's correlation for all these parameters are actually given here. So it appears that the Pearson's correlation for all parameters are actually statistically significant, telling us that there are evident relationship between all these parameters. This is actually a crucial step, telling us that these are the correct parameters that we have reselected, and they have relationship with the dependent variables in this case, which is actually the slaughter weight. This is actually the first series of results when the data are being entered using the enter method. The enter method tells us that all these parameters are being included all at the same time. So the first table here tells us all the variables are included. So what are the variables that are being included? Post-weaning ADG, birth weight, weaning weight. So always look at the subscripts in this case, the footnote and the subscripts in this case. It will tell you what are the parameters that has been included for comparison. So table number 2 will tell us the model summary. So this model summary tells us that this particular model, inclusive of predictor, post-weaning weight, birth weight, and weaning weight, actually explains 62.7% of all the variations seen in this model. And based on the Durbin-Watson's value, we can conclude that there are no autocollinearity present because the values lies between 1.5 to 2.5. And in this case, it also tells you that you are using these parameters indicated in superscript A to predict the slaughter weight. So we are actually on the right track. The next table is actually even more crucial because it tells us that what will be the combined effect of the predictors comprising of constant, post-weaning weight, birth weight, and weaning weight in terms of how they influence the slaughter weight. And you can see from here, the regression model are actually significant, meaning that there is actually an evident relationship. But is there a way for us to improve this relationship or maybe dissect how individual parameters affect the slaughter weight? So this is actually where we need much more detailed modeling, as we already indicated earlier, using the stepwise method. This particular sets of results here tell us the stepwise entry method. As you can see here, stepwise method, we only have the inclusion of 2 parameters. So in this case, you can see the post-weaning ADG is actually not included. Why? Because the value actually exceeded the threshold, which is actually the criteria used for stepwise inclusion. This is actually a very important step and one reason why stepwise is commonly used in this case. As usual, we'll be looking at how many parameters that has been included, indicated here. What will be the R-square for the 2 models that is being used here in this case? So you can see here, the R-square tells you that if you use only model 1, weaning weight, then which is indicated by the weaning weight A here, then you can only explain 58.6% of the variation seen. However, if you use model 2, which is actually comprising of predictor, constant, weaning weight, and birth weight, you can explain around 67.6% of all variation seen. Recall that this is actually much higher than the earlier model where you use the enter method, whereby you can only explain 62.7%. Of course, for a model to be accurate, you need your model to be able to explain as much as possible of the variation seen within your dependent variable. So obviously, the stepwise method is a good choice in this particular approach. So you can see here that by adding the birth weight, you can actually add maybe another 9 or 10% the ability for the model to explain all variation detected in this particular model. So again, it is so important for us to know what will be the dependent variable, what will be the predictors considered here by looking at the superscripts in this case. So you can see in model 1, again, we only have the constant and winning weight, meaning this is actually a simple model as already exemplified earlier. And then C is actually a model 2, which is comprising of two parameters, winning weight, birth weight, plus its constant. So you can see here, both models are equally good. But since we want more detail in terms of how much of variation that can be explained, we will automatically go for model 2. Now, having model 2, it becomes important for us to know which of the one of the two parameters chosen here between winning weight and birth weight are much more important in determining the slaughter weight itself. And in order to do this, we can actually read the standardized coefficient beta. Standardized coefficient beta can actually allow us to understand which of the two parameters is actually more important in terms of contribution to the prediction of the slaughter weight itself. At the same time, pay attention to the tolerance and the VIF numbers as what we already discussed earlier. As you can see, the tolerance or the T value and VIF or 1 over T value tells us that there are no apparent collinearity violations. So that means our models are good because it fulfills all the assumptions. At the same time, do pay attention to the significance value here, telling us again that both winning weight and birth weight are significant contributor and they contribute statistically significant effects to the slaughter weight that we're going to see. Recall that we have a third parameter, which is actually a post-winning weight, which was not discussed here. So where did it go? This is actually something that we need to be mindful as well. Before we move on to talk about where did the post-winning ADG goes, let's complete this particular model. So in this sense, this model 1 can be written as slaughter weight equals 3.584 winning weight plus 68.787. Remember, model 1 only explains roughly about 58% of the variation seen. Model 2, which is actually much better, explaining 67% of the variation seen, can be written as slaughter weight equals 2.284 multiplied by winning weight plus 13.802 birth weight plus 65.225. And you can see here, again, by looking at the beta coefficient, we know that the winning weight actually contributed more to the changes in this particular model itself. So that means winning weight is actually something that you should not neglect. This is something that will be important for us to remember. If let's say you will ever use multiple regression to predict a disease risk, or maybe to model certain diseases, or to model certain risk or certain behavior, then you need to know what will be the factors that contributed a lot to your model. Now, let's revisit the missing post-winning ADG. This is actually where it comes up. Recall that it is also included, but it is not taken into account of the model. Why? Because in our stepwise model, it has automatically been excluded because it is not significant. So by going for stepwise method, we are actually asking the computer to exclude variables. So it would be good for us to look at the variables that has been excluded. So in this case, you can see that it is evidently not significant, and therefore it is not expected to play roles at all in contributing to the further accuracy of the model. And further down, you can see that further description of the collinearity diagnostics here, taking into account the eigenvalue and the condition index, which we already discussed at the beginning of these slides, tell us that there are no apparent collinearity violations. So please refer to the earlier slides on what will be the value of the condition index that is actually considered acceptable for multiple regression. Then again, another factor that we should also be consider will be the residual analysis. Recall that residual analysis is actually allowing us to look for outliers, and of course, to ensure that all the variables are actually normally distributed. How do you ensure that? In order to do that, you must have the residual data distribution pattern that is randomly distributed. Okay, randomly distributed. So in this case, the residual analysis showed us the goodness of fit of the primary model. So this tells you in a brief manner that your model is actually a very good predictor. Okay, a very good predictor. So based on this, you can actually use the model that you have already constructed earlier, which is SW equals 2.24 WW plus 13.802 BW plus 65.225 to predict the slaughter weight once you know the winning weight and the birth weight. So you can see here indicated by this blue formula here, it will be actually the slaughter weight that you can predict once you know what will be the winning weight and what will be the birth weight. And the residual analysis and condition index that is being given on this page and the prior page only tells you that your model is actually reliable. So this is again the scatter plot, further reinforcing the fact that you are your residual analysis is actually randomly distributed. So this is actually what I meant by residual analysis having a good fit, telling you that model having a good fit. So if they are having a good fit, there should be random distributions of the residual analysis dots plotted between standardized residual regression and regression standardized predicted value. So this is actually the standardized value and residual value versus their predicted value. So if let's say they are being distributed randomly, that means the model has good reliability. But if you started to get clustering, like what is going to be depicted in this particular page, then your model will have issues in terms of validity of the prediction. So you can see here, the vertical axis indicate to you standardized residual, whereas horizontal axis indicates standardized predicted value. So on the extreme top left, you can see here, that will be telling you that what we actually wanted, a random homoscedastic data, which conforms to regression, and therefore the model and the analysis can be trusted. What we do not want will be the other 5 tape panel. So if you have bias but homoscedastic, then the residuals will be depicted in that particular form. Non-linear and homoscedastic, it will be arched. And then random heteroscedastic, remember heteroscedastic is the opposite of homoscedastic, then it will exist in the fan pattern. Same with bias heteroscedastic and non-linear heteroscedastic. So you can always see that one hallmark of heteroscedasticity is that the dots actually fan out. But depending on whether it is actually biased or non-linear, the way that the dots fan out will differ. So what we actually wanted is actually just the panel on the extreme top left. Okay, top left, telling us that our model is usable, our model is valid.